audio recording for visually impaired students from the book Pradeep's Inorganic Chemistry by Dr. K. Bhasin. Chapter 3 S Block Elements. The S Block elements consist of metals contained in Group 1 and Group 2 of the periodic table. These two groups are referred to as S block because the elements in them have a valence shell electronic structure of noble gas NS1 Group 1 and noble gas NS2 Group 2. Group 1 contains the elements lithium to francium and Group 2 contains the elements beryllium to radium. Metals you came across in daily life are generally considered to be dense and non-reactive, but here is group of metals we are going to study that are less dense and highly reactive. In this unit, we shall look at the properties of these two groups of metals which are distinctly different from the conventional metals. Heading 3.1 Electronic Configurations. The elements of Group 1 and Group 2 of the periodic table constitute the S block elements. The electronic configurations of these elements are given together in Table 3.1. Table 3.1 Electronic configurations of S block elements. Group 1 Alkali metals. Element lithium, atomic number 3, electronic configuration helium 2s1. Sodium, atomic number 11, electronic configuration neon 3s1. Potassium, atomic number 19, electronic configuration argon 4s1. Rubidium, atomic number 37, electronic configuration krypton 5s1. Cesium, atomic number 55, electronic configuration xenon 6s1. Francium, atomic number 87, electronic configuration radon 7s1. Group 2 Alkaline earth metals. Element beryllium, atomic number 4, electronic configuration helium 2s2. Magnesium, atomic number 12, electronic configuration neon 3s2. Calcium, atomic number 20, electronic configuration argon 4s2. Strontium, atomic number 38, electronic configuration krypton 5s2. Barium, atomic number 56, electronic configuration xenon 6s2. Radium, atomic number 88, electronic configuration radon 7s2. The elements constituting Group 1 are reactive metals and form strongly alkaline oxide and hydroxides. Therefore, they are called alkali metals. The elements belonging to Group 2 are also metals and are commonly known as alkaline earth metals. The oxides of some of these metals were known much earlier than the metals themselves, and they are called alkaline earths since they were alkaline in nature and existed on the earth. Heading 3.2 General characteristics of alkali metals. The alkali metals belonging to Group 1 of the periodic table are lithium, sodium, potassium, rubidium, cesium, and francium, with respective atomic numbers 3, 11, 19, 37, 55, 87. Their general electronic configurations is noble gas NS1. They form a closely related group and probably have the least complicated chemistry of any group in the periodic table. The physical and chemical properties of the elements are closely related to their electronic structures and sizes. The elements are all metals, good conductors of electricity, and are typically soft and highly reactive. They have one loosely held valence electron in their outer shell and typically form univalent ionic and colorless compounds. The hydroxides and oxides are very strong bases and their oxosols are very stable. Let us have a close look on the physical and chemical properties of Group 1 elements as given in Table 3.2. Physical properties. All the elements of Group 1 are silvery white, soft and light metals. Some of their important physical constants are summed up in Table 3.2. Table 3.2 Physical properties of alkali metals. Property atomic number lithium 3, sodium 11, potassium 19, rubidium 37, cesium 55. Atomic mass lithium 6.94, sodium 22.99, potassium 39.10, rubidium 85.48, cesium 132.91. Density at 20 degrees Celsius in gram per cc. Lithium 0.534, sodium 0.972, potassium 0.859, rubidium 1.530, cesium 1.903. Atomic volume in Cc: lithium 12.97, sodium 23.68, potassium 45.36, rubidium 55.80, cesium 69.95. Melting point in degree Celsius: lithium 180, sodium 97.8, potassium 64.0, rubidium 39.0, cesium 28.5. Boiling point in degree Celsius: lithium 1326, sodium 883, potassium 756, rubidium 688, cesium 690. Specific heat at 0 degrees Celsius in calorie per gram: lithium 0.941, sodium 0.293, potassium 0.17, rubidium 0.08, cesium 0.049. Atomic radius in Armstrong: lithium 1.34, sodium 1.54, potassium 1.96, rubidium 2.11, cesium 2.25. Ionic radius in Armstrong: lithium 0.60, sodium 0.95, potassium 1.33, rubidium 1.48, cesium 1.69. Heat of atomization in kilojoule per mole: lithium 159.0, sodium 108.1, potassium 90.2, rubidium 82.1, cesium 78.2. Ionization energy in kilojoule per mole: lithium 520.1, sodium 495.2, potassium 418.7, rubidium 403.0, cesium 375.7. Electronegativity: lithium 1.0, sodium 0.9, potassium 0.8, rubidium 0.8, cesium 0.7. Flame coloration: lithium crimson red, sodium golden yellow, potassium violet, rubidium violet, cesium violet. First, size of atoms and ions. Alkali metals have the largest atomic sizes in their corresponding periods. When the outermost electron is removed to give a positive ion, the size decreases considerably. It is because after the removal of outermost electron, the positive charge on the nucleus becomes greater than the charge on the remaining electrons. Thus, each of the remaining electrons is attracted more strongly towards the nucleus and reduces the size. The size of the cations formed are smaller than the parent atom. Similarly, the ions formed from the other alkali metals are smaller than the parent atoms. However, the size of the cation increases in size from lithium to cesium as extra shells of electrons are added. The electronic configurations of the alkali metals ions would evidently be similar to those of noble gases, since they have no unpaired electrons. These ions are diamagnetic and colorless. Second, density. Alkali metals are large in size, so group 1 elements have remarkably low densities. Density of a metallic element depends upon the type of packing of atoms in the metallic phase as well as on the size. Alkali metals have close packed metal atoms in their lattices, and because of the comparatively large size of these atoms, they have low densities. As can be seen from table 3.2, density gradually increases on moving down from lithium towards cesium. Potassium, however, is lighter than sodium. Lithium, sodium, and potassium are even lighter than water. It is, however, unusual for metals to have low densities. If you recall, most of the transition metals have densities greater than 5 gram per centimeter cube. Iron has a density of 7.9 gram per centimeter cube, while mercury has a density of 13.6 gram per centimeter cube. Third, ionization energies. The first ionization energies for the atoms in this group are appreciably lower than those for any other group in the periodic table. The atoms are very large, so the outermost electrons are only held weakly by the nucleus. Hence, the amount of energy needed to remove the other outer electron is not very large. Further, as the atomic radius increases on moving down the group, the outer electron gets farther and farther away from the nucleus, and therefore ionization energy decreases on moving down the lithium down from lithium towards cesium. The second ionization energy is the energy required to remove the second electron from the atom. The second ionization energy is always larger than the first because it involves removing an electron from a smaller positive ion rather than from a largest neutral atom. The alkali metals commonly form univalent M positive ions only. On account of their low ionization energies, these metals have great tendency to lose their valence electrons and thus change into positive ions. M gives out M positive ion plus electron. These elements are therefore said to have strong electropositive character. Since ionization energy decreases on moving down the group, the electropositive character increases on moving down the group. These elements are so highly electropositive that they emit electrons even when exposed to light, photoelectric effect. This property is responsible for their use in photoelectric cells. Fourth, electronegativity and bond type. Since these metals are highly electropositive, their electronegativities, that is, their tendency to attract electrons, are very low, and the value of electronegativity decreases as we move from lithium to cesium. When these elements react with other elements to form compounds, a large electronegativity difference between the two atoms exists, and consequently ionic bonds are formed. An electronegativity difference of approximately 1.7 to 1.8 corresponds to 50% ionic character. In case of sodium chloride, the electronegativity difference is 2.1, 3.0 to 0.9, and thus the bonding is predominantly ionic. Similarly, compounds formed by other alkali metals are also ionic. Fifth, melting points. All the alkali metals are soft and have low melting points. As they have only one valence electron per metal atom, the energy binding the atoms in the crystal lattice of the metal is relatively low. The melting points invariably decrease in moving down from lithium to cesium. This decrease is due to the increase in the size of the atom of the element. Sixth, boiling points. The boiling points also decrease in the same order as the melting points. The boiling point of the lithium is 1326 degrees Celsius, while that of cesium is 690 degrees Celsius. Seventh, hydration of ions. The smaller the size of the ion, the greater is the degree of hydration. Amongst alkali metals ions, lithium positive ion is the smallest in size and thus has highest charge or size ratio amongst the alkali metal ions and gets much more easily hydrated. It means it can hold more water molecules in its hydration sphere than rest of group 1 elements. As a result of this difference in degree of hydration, ionic radii of hydrated alkali metal ions decreased from lithium positive to cesium positive. Thus, lithium positive ion, which should have been smallest, is actually largest in size in aqueous solutions. Therefore, the ionic radii of alkali metal ions in aqueous solution decreases in the order. Lithium positive is the highest, then sodium positive, then potassium positive, then rubidium positive, and cesium positive is the least. As a result, lithium positive ion has the lowest and the cesium ion has the highest mobility in an electric field. 8th, oxidation states. As they have one valence electron, all the alkali metals exhibit an oxidation state of +1. The second ionization energy is so high that the second electron is very rarely lost. Ninth, reducing properties and oxidation potentials. Reduction is a process in which electrons are gained, and oxidation is a process in which electrons are lost. An oxidizing agent is a substance which can accept electrons, while a reducing agent is a substance which can lose electrons. Let us consider the formation of sodium chloride from elemental sodium and gaseous chlorine. As sodium has low ionization energy, it can readily lose electron, while chlorine has high electron affinity and can accept electrons more readily. Thus, sodium is a reducing agent and chlorine is an oxidizing agent. Sodium here on heating gives sodium gaseous, and sodium when gives sodium positive gas and electron. Half Cl2 gaseous plus electron gives out Cl negative gaseous. Na positive gaseous plus Cl negative gaseous gives out Na positive Cl negative, that is NaCl, and the overall result of the reaction is Na plus half Cl2 gives out Na positive Cl negative. Thus, an element which is a reducing agent must have low ionization energy. On the other hand, an element with high ionization energy is a strong oxidizing agent. Since ionization energy decreases on moving down from lithium to cesium, the reducing property increases down the group. The tendency of an element to lose an electron in solution is measured by the standard oxidation potential of the element. The standard oxidation potential of the alkali metals are given in table 3.3. Table 3.3, Standard oxidation potentials of alkali metals. Element lithium. Oxidation reaction, lithium gives out lithium positive ion plus electron. Standard oxidation potential in volt 3.04. Sodium oxidation reaction, sodium gives out sodium positive ion plus electron. Standard oxidation potential 2.71 volt. Potassium oxidation reaction, potassium gives out potassium positive ion plus electron. Standard oxidation potential 2.92 volt. Rubidium gives out rubidium positive ion plus electron. Standard oxidation potential 2.99 volt. Cesium gives out cesium positive ion plus electron. Standard oxidation potential 3.02 volt. As can be seen from the table 3.3 that alkali metals have high values of standard oxidation potentials, thus have strong tendency to act as reducing agents. Lithium is the strongest reducing agent. This is opposite to what we expected on the basis of values of ionization energies. It has been already discussed that the lithium has highest ionization energy and holds its electron most tightly. This at first sight seems to be contrary to the maximum value of oxidation potential of lithium, which indicates that lithium gives off its electron most readily. This can be explained if we recall that ionization energy is the property of an isolated atom in the gaseous state, while oxidation potential concerns itself with the metal as it goes into solution. Ionization energy involves only the following change. Metal in gaseous gives out metal positive plus electron. Oxidation potential, on the other hand, involves the process metal in elemental state gives out metal positive aqueous plus electron, which takes place in three consecutive steps. Metal gives out metal gaseous, delta HS. Metals give out metal positive plus electron, IP. Metal positive plus H2O gives out metal positive, that is delta H hydration. In the first step, the metal is evaporated to gaseous state. The energy required in this process is called sublimation energy, delta HS, which is about the same for all the alkali metals. In the second step, ionization energy comes into play, which is highest for lithium. In the third stage, the gaseous ion gets hydrated. In this process, hydration energy gets liberated. The oxidation potential, which gives the tendency for the overall change to occur naturally, depends on the net effect of all three steps. Energy is equal to delta H plus I plus delta H hydration. Lithium ion is hydrated to the maximum extent because energy liberated in third step is maximum for lithium positive ion. The hydration energy of lithium positive ion is so large that it compensates the energy required to knock off the electron in step 2. Thus, lithium has higher oxidation potential than rest of the members. 10th, characteristic flame coloration. Alkali metal and their salts impart characteristic flame coloration. The alkali metals have been shown to have low ionization values. The energy from the Bunsen flame is sufficient enough to excite the electrons of alkali metals to higher energy. The excited state is unstable, and when the excited electron comes back to the original energy level, the energy is released in the form of visible radiation. Each alkali metal undergo its own unique electron transition. For example, the yellow color of sodium is the result of energy emitted when an electron drops from 3p1 orbital to 3s1 orbital of a neutral sodium atom. The alkali metals and their characteristic flame colors are given below. Metal lithium, color crimson red, sodium yellow, potassium lilac, rubidium red violet, cesium blue. 11th, lattice energies. Salts of alkali metals are ionic in nature, consisting of cations and anions. The lattice energy of an ionic solid is the energy released when cations and anions in gaseous state are brought closer from infinity to their respective crystal sites to form 1 mole of the ionic crystal. Lithium positive plus Cl negative gives out Li positive Cl negative. Delta H is equal to lattice energy of Li positive Cl negative. Cesium positive plus chlorine negative gives out cesium positive chlorine negative. Delta H is equal to lattice energy of cesium chloride, cesium positive Cl negative. Due to strong electrostatic attraction between oppositively charged ions, lattice energies of ionic solids are quite high. Since Coulombic forces of attraction vary directly as the product of the charges, it follows that the higher the charge on the ions, the greater is the lattice energy of the ionic solid. Thus, lattice energy of lithium fluoride is 1034 kJ per mole, while that of cesium fluoride is 743.9 kJ per mole. As a general rule, lattice energies of salts of alkali metals having a given anion decrease with increase in atomic number of the alkali metal as shown below. Alkali metal chlorides. Lithium chloride. Lattice energy in kilojoule per mole 802. Sodium chloride 758. Potassium chloride 681. Rubidium chloride 660. Cesium chloride 618. Sodium halides. Sodium fluoride. Lattice energy in kilojoule per mole 895. Sodium chloride 758. Sodium bromide 715. Sodium iodide 669. Chemical properties. Alkali metals with low ionization energies and relatively low heats of atomization exhibit high chemical reactivity. The important chemical properties and their trends are discussed below. First, action of air. Group 1 elements tarnish rapidly in dry air due to the formation of oxides at their surface. They are therefore always kept under kerosene or paraffin oil to protect them from the action of air. They burn vigorously in air or oxygen, forming oxides. Lithium forms the monoxide Li2O, sodium forms the peroxide Na2O2, and the rest of the elements form superoxides MO2. Second, action of water. They react readily with water forming hydroxides and evolving hydrogen gas. 2Li plus 2H2O gives out 2LiOH plus H2. As the electropositive character increases down the group, the reactivity with water increases on descending the group from lithium to cesium. Third, 3. Action with hydrogen. These metals react with hydrogen and form ionic or salt-like hydrides M positive, H negative. However, the ease with which they do so decreases from lithium to cesium. The hydrides contain the H negative ion. The hydrides react with water, liberating hydrogen, and lithium hydride is used as a source of hydrogen for military purposes and for filling meteorological balloons. LiH plus H2O gives out LiOH plus H2. The hydrides behave as strong reducing agents and their reducing nature increases down the group. Fourth, action with halogens. They combine readily with halogens and form halides of type M positive, X negative. Example, 2Li plus Cl2 gives out 2Li positive, Cl negative. The alkali metal halides react with the halogens and interhalogen compounds forming ionic polyhalides. Fifth, solubility in mercury. Alkali metals dissolve readily in mercury forming what are called amalgams. The process is highly exothermic. Sixth, solubility in liquid ammonia. Alkali metals dissolve in liquid ammonia to give blue solutions, which on standing slowly evolve hydrogen. 2M plus 2NH3 gives out 2MnH2, which is alkali metal amides plus H2 gaseous. The dissolution of metal in ammonia is accompanied by its ionization. M gives out M positive plus electron. The ammonia molecules solvate the cation as well as the electron as follows. M plus NH3 in excess gives out ammoniated cation, which is MNH3X positive plus electron NH3Y ammoniated electron. The value of X and Y depend upon the extent of solution of the alkali metal ion and the electron respectively. It is the ammoniated electron which is responsible for the blue color of the solution. The electrical conductivity is due to the ammoniated cation as well as the ammoniated electron. Due to the presence of the free or ammoniated electron, these solutions behave as strong reducing agent. The dilute solutions are paramagnetic due to the presence of free electrons. The decrease in paramagnetic character with increased concentration suggests the electron pairs are formed in concentrated solutions. On standing for longer period of time, the solution liberates hydrogen as 2M plus 2NH3 gives out 2MnH2, which is metal amide plus H2. Heading 3.3, General Characteristics of Group 2 Elements. The alkaline earth metals. The alkaline earth metals belonging of Group 2 of the periodic table are beryllium, magnesium, calcium, strontium, barium, and radium. They are called alkaline earth metals because their oxide occur in Earth's crust and their hydroxide are strongly alkaline. The group 2 elements show the similar trends in properties as were observed in case of group 1 elements. However, beryllium stands apart from the rest of the group and differs much more from rest of the members than lithium does from the rest of group 1. The main reason is that the beryllium atom and beryllium 2 positive ion are both extremely small and the relative increase in size from beryllium 2 positive to magnesium 2 positive is nearly 4 times greater than the corresponding increase between lithium positive and sodium positive. Beryllium, like lithium, also shows diagonal relationship. The elements forms a series of highly reactive metals but are less reactive than group 1. They are divalent and generally form colorless ionic compounds. The oxides and hydroxides of alkaline earth metals are less basic than those of group 1. Magnesium is an important structural metal. Magnesium 2 positive and calcium 2 positive ions are essential elements in the human body. In addition, magnesium is an important constituent of chlorophyll. General electronic configuration of group 2 metals is Ns2. Let us discuss the physical and chemical properties of group 2 elements. Table 3.4. Physical properties of alkaline earth metals. Property. Atomic number. Beryllium 4, magnesium 12, calcium 20, strontium 38, barium 56, radium 88. Atomic mass. Beryllium 9.10, magnesium 24.31, calcium 40.08, strontium 87.62, barium 137.34, radium 226. Atomic radius in Armstrong. Beryllium 1.12, magnesium 1.60, calcium 1.97, strontium 2.15, barium 2.22. Ionic radius in Armstrong. Beryllium 2.27, magnesium 0.72, calcium 1, strontium 1.18, barium 1.35. Density in gram per centimeter cube. Barium 1.84, magnesium 1.74, calcium 1.05, strontium 2.03, barium 3.62, radium 5.5. Ionization energy in kilojoule per mole. First, for beryllium 899, magnesium 737, calcium 590, strontium 549, barium 503, radium 509. Second ionization energy, barium 1757, magnesium 1450, calcium 1145, strontium 1064, barium 965, radium 979. Third ionization energy, for beryllium 14,847, magnesium 7,731, calcium 4,910, and for radium 3281. Oxidation state, for all it's plus 2. Melting point in degrees Celsius, beryllium 1287, magnesium 649, calcium 839, strontium 768, barium 727, radium 700. Boiling point in degrees Celsius, beryllium 2500, magnesium 1105, calcium 1494, strontium 1381, barium 1850, radium 1700. Electronegativity, barium 1.5, magnesium 1.2, calcium 1.0, strontium 1.0, barium 0.9. Physical properties. First, size of atoms and ions. Group 2 elements have large atomic size but are smaller than the corresponding group 1 elements as the extra charge on the nucleus pulls the orbital electrons in. Similarly, the ions are large but are smaller than those of group 1 elements. The alkaline earth metals ions are diamagnetic and colorless. The outer electronic configurations of the ions being stable, they resist the removal of further electrons. Therefore, the oxidation state is invariably plus 2 in all its compounds. Second, density. Alkaline earth metals have relatively low densities but are more dense than alkali metals. It is because their atomic sizes are smaller than the corresponding alkali metals. Density decreases slightly on moving down the group into calcium, but it increases considerably thereafter into up to radium. Third, melting points and boiling points. Melting points and boiling points do not show regular trends, however, they are higher than those of alkali metals. Fourth, metallic properties. Group 2 elements are typical metallic in nature. They show good metallic luster and possess high electrical and thermal conductivity. Fifth, hardness. These are moderately hard, although they are harder than alkali metals, yet they can be cut with a sharp knife. Sixth, ionization energy. Alkaline earth metals have low ionization energy, energy values due to the larger size of the atoms. The ionization energy decreases down the group because the progressive increase in size of the atom from beryllium to radium. Since the alkaline earth metals are smaller than those of alkali metals, the electrons are more tightly held in alkaline earth metals and the energy needed to remove the first electron is greater than in alkali metals. Although the first ionization energy values of alkaline earth metals are higher compared to the alkali metals, the second ionization energy values of alkaline earth metals are much smaller than those of alkali metals. Table 3.2 and Table 3.4. This is because in case of alkali metals, the second electron is to be removed from the cation M positive, which has acquired a stable electronic configuration. In case of alkaline earth metals, the second electron is to be removed from the outermost shell, which is far easier to be removed. However, to remove an electron from the alkaline earth bivalent ion M2 positive, a very high amount of energy is required. This is because the third electron is to be removed from the cation M2 positive, which has already acquired a noble gas configuration. Seventh, electronegativity. The electronegativity values of group 2 elements are low but are higher than the values for group 1. Thus, when magnesium, calcium, strontium, and barium react with the halogens and oxygen, the electronegativity difference being large between them, the compounds formed are ionic. Eighth, hydration of ions. The hydration energies of the group 2 ions are 4 or 5 times greater than for group 1 ions. This is largely due to their smaller size and increased charge. Hydration energy values decreases with increase in atomic number down the group. As a result, the crystalline compounds of group 2 contain more water of crystallization than the corresponding group 1 compounds. Thus, NaCl and KCl are anhydrons, whereas MgCl2.6H2O and CaCl2.6H2O and BaCl2.2H2O all have water of crystallization. Table 3.5 Hydration energies of group 2 ions. Elements beryllium 2 positive. Ionic radius in Armstrong 0.31. Delta H hydration in kilojoule per mole minus 2494. Magnesium 2 positive. Ionic radius 0.72. Delta H hydration minus 1921. Calcium 2 positive, ionic radius 1, delta H of hydration minus 1577. Strontium 2 positive, ionic radius 1.18, delta H hydration minus 1443. Barium 2 positive, ionic radius 1.35, delta H hydration minus 1305. Ninth, electropositive character. Alkaline earth metals have low ionization energy values and are strongly electropositive in nature. These elements, although fairly strongly electropositive, are not as strongly electropositive as the metals of group 1. As ionization energy decreases on moving down the group, the electropositive character increases on moving from beryllium to barium. Nth, reducing properties, oxidation potentials. Group 2 elements have a strong tendency to form bivalent cation. Hence, they are strong reducing agents. The oxidation potential, which is a measure of the tendency of an element to lose electrons, increases on moving down the group, as shown in Table 3.6. Table 3.6 Standard oxidation potentials of alkaline earth metals. Element beryllium. Oxidation reaction. Beryllium gives out beryllium 2 positive ion plus 2 electron. Standard oxidation potential 1.85 volt. Magnesium. Oxidation reaction. Magnesium gives out magnesium 2 positive ion plus 2 electron. Standard oxidation potential 2.37 volt. Calcium. Oxidation reaction. Calcium gives out calcium 2 positive ion plus 2 electron. Standard oxidation potential 2.87 volt. Strontium. Strontium gives out strontium 2 positive ion plus 2 electron. Standard oxidation potential 2.89. Barium. Oxidation reaction. Barium gives out barium 2 positive ion plus 2 electron. Standard oxidation potential 2.90 volt. 11. Flame coloration. When energy is supplied to these elements in a flame, their electrons are excited to higher energy states, as in the case of alkali metals. When the electrons drop back to the original energy level, the extra energy is emitted in the form of visible light with characteristic colors as given below. The alkaline earth metals impart the following characteristic colors in the flame. Calcium gives out brick red, strontium gives out crimson red, barium gives out grassy green, and radium gives out blue. Beryllium and magnesium, being smaller in size, do not permit the strongly bound electrons to get excited to higher energy level in the flame. Thus, they do not give any color in Bunsen burner. Chemical properties. The important chemical properties of group 2 elements are as follows. First, action of air and water. Group 2 elements, being less electropositive than the alkali metals, are less reactive. Thus, they are slowly oxidized on exposure to air. However, they burn in oxygen to form ionic oxide (MO), whereas barium and radium form peroxides. 2m plus O2 in the presence of heat gives out 2MO, that is metal oxide. M is equal to beryllium here, that is Mg or calcium. M plus O2 gives out MO2 metal peroxide. M here is barium or strontium. They react slowly with water to liberate hydrogen and form hydroxides. Calcium plus 2 H2O gives out CaOH whole twice plus H2. Magnesium does not react with cold water but it decomposes hot water. Mg plus 2H2O gives out MgOH2 plus H2, or Mg plus H2O gives out MgO plus H2. Despite the favorable reduction potential, magnesium does not react readily with water unless the oxide layer is removed by amalgamating with mercury. Second, action with hydrogen. All the elements except beryllium combine with hydrogen to form hydrides of the formula MH2. Beryllium hydride is difficult to prepare and is less stable than the other hydrides. Impure BeH2 was first made by reducing beryllium chloride with LiAlH4, that is lithium aluminium hydride. The hydrides are all reducing agents and are hydrolyzed by water and dilute acids with the brisk evolution of hydrogen. CH2, SRH2 and BH2 are ionic, while hydrides of beryllium and magnesium are covalent and polymeric. Polymeric BeH2 and presents in interesting structural study as shown in figure 3.1. In gas phase, several species may be present comprising of polymeric chains and rings. The solid is polymeric and its X-ray structure shows that it contains chains and hydrogen bridges between beryllium atoms. This is an example of cluster compound where monomeric molecule BeH2 is electron deficient, and by clustering each atom share its electron with several neighbors and receives a share in their electrons. The bonding in the hydrides cannot be explained by conventional two electrons covalent bond. It can only be explained by involving the concept of three centers two electrons bonds, 3C 2 electron, known as banana bond. Third, action with nitrogen. These elements burn in nitrogen to form nitrides M3N2, which react with water to liberate ammonia. B3N2 is volatile, whereas other nitrides are non-volatile. Fourth, action with halogen. Halide of the type MX2 are made by heating the metals with the halogens. Beryllium halides are covalent. Halides of other elements are electrovalent and readily dissolve in water. The anhydrous halides are polymeric. Beryllium chloride vapor contains BeCl2 monomeric and dimeric BeCl2 whole 2, but the solid is highly polymerized. As can be seen from the figure 3.2, the structure of BeCl2 whole N polymer is similar to that of BeH2, but the bonding is different. Both show clustering, but the hydride has 3 center 2 electron bonding, whereas halides have halogen bridges where halogen atom bonded to one beryllium atom donate a lone pair of electrons to form a coordinate bond to another beryllium atom. Fifth, action of acids. On account of their high oxidation potentials, these metals readily liberate hydrogen from dilute acids. Heading 3.4, diagonal relationship. One of the important features of the elements of the second period of the periodic table is that they resemble with the elements to their lower right in the third period, that is diagonally opposite element. More than their own congeners, the diagonal relationship is shown by following pair of electrons of the periodic table. Cause of diagonal relationship. The basic cause for the diagonal relationship arises because of the similarity in their properties between the diagonal elements. Electropositive character. The electropositive nature of the elements increases on descending a group and decrease as we move from left to right in a period. Therefore, on moving diagonally, the two opposing tendencies of increasing and decreasing almost cancel out each other. As a result, the diagonal elements have almost same electropositive character. Polarizing power. When we move from left to right in a period, the ionic charge increases whereas the ionic radius decreases. This results in the increase of polarizing power. On the other hand, when we move from top to bottom in a particular group, the ionic charge remains the same, while the ionic radius increases. This results in the decrease of polarizing power. However, on moving diagonally, these two opposing tendencies along a period and down a group cancel each other. As a result, the diagonal elements have almost similar polarizing power. Next heading 3.5, Diagonal relationship of lithium with magnesium. This diagonal relationship is due to similar polarizing powers of Li positive ion and Mg2 positive ion. Lithium is smaller than sodium and magnesium in turn is also smaller than sodium. However, lithium and magnesium are smaller in size. The sizes of Li positive 0.76 Armstrong and Mg2 positive 0.72 Armstrong ions are comparable, and in situation where size is important, their behavior should be similar. It has also been suggested that the diagonal relationship arises because of a diagonal similarity is electronegativity values. Lithium exhibits diagonal similarity with magnesium. Some of common characteristics between Li and Mg are listed below. First, atomic radius of lithium 1.34 Armstrong and magnesium 1.364 Armstrong are nearly similar. Second, the radii of lithium positive ion 0.76 Armstrong and magnesium 2 positive 0.72 Armstrong are quite closer to each other. Third, polarizing powers of lithium positive ion and magnesium 2 positive ion are about the same magnitude. Fourth, the electronegativities of lithium and magnesium being 1.0 and 1.2 respectively are not much different from each other. Fifth, like magnesium, lithium hardly reacts with liquid bromine. Sixth, like magnesium, lithium decomposes water only slowly liberating hydrogen. Seventh, both lithium and magnesium form nitrides on heating with nitrogen. Eighth, both lithium and magnesium form normal oxide rather than peroxide on burning in oxygen. Ninth, lithium nitrate, like magnesium nitrate, involves nitrogen dioxide and oxygen on heating, leaving behind the oxide. 10th, the chlorides of both lithium and magnesium undergo hydrolysis in hot water. 11th, lithium chloride, like magnesium chloride, is diliquescent. 11th, lithium chloride and magnesium chloride is diliquescent. 12th, the carbonates, phosphates, fluorides, and oxalates of lithium and magnesium are sparingly soluble in water. 13th, lithium hydroxide, like magnesium hydroxide, is a weak base. 14th, lithium and magnesium carbonates decompose on heating to give oxides. It is important to note that carbonates of other alkali metals do not decompose on heating. 15. Lithium and magnesium hydroxide decompose on heating to give oxides. Hydroxides of other alkali metals, however, are stable to heat. Diagonal relationship of beryllium and aluminium. Beryllium and aluminium also show diagonal relationship. Here the sizes are not close. Beryllium 2 positive is equal to 0.45 Armstrong and aluminium 3 positive 0.535 Armstrong. But the charge per unit area is similar. Beryllium positive is 2.36 and aluminium 3 positive is 2.50 because the charges on beryllium and aluminium are 2 positive and 3 positive respectively. Charge per unit area is equal to ionic charge upon 4 by 3 pi into ionic radius square. In addition, the electronegativity of beryllium matches with that of aluminium. Resemblance between beryllium and aluminium. First, beryllium atom is small and therefore has high charge density. It has therefore a strong tendency to form covalent compounds. Aluminium too has a strong tendency to form covalent compounds. Second, standard oxidation potential of these elements are quite closer to each other. Third, both are rendered passive by dilute HNO3 because of the formation of oxide film. Fourth, beryllium oxide, like aluminium oxide, is amphoteric. It dissolves in acid as well as in alkalis. Fifth, both dissolve in sodium hydroxide with the evolution of hydrogen gas. Sixth, both form extremely hard carbides which evolve methane on treatment with water. Seventh, the halides of beryllium and aluminium are soluble in organic solvents. Eighth, chlorides of both beryllium and aluminium have bridged polymeric structure. Ninth, their halides are used in Friedel-Crafts reaction. Next heading 3.6, the hydrides of S block elements. The hydrogen atom consists of a single proton and an electron in its native state. Under normal conditions, elementary hydrogen exists as a diatomic molecule H2 in the gaseous state. Hydrogen is known to form binary compounds with almost every element of the periodic table. All binary hydrogen compounds are called hydrides. The hydrides contain the H negative ion. A number of hydrides are known and can be classified into following classes. First, salt-like or ionic hydrides. Second, covalent hydrides. Third, borderline hydrides. Fourth, transition metal hydrides. The ionic hydrides. Ionic hydrides are formed by the alkali metals and alkaline earth metals. They can be prepared by the direct combination of elements on heating in the 150 to 700 degree range. These species may be represented as M positive H negative or M2 positive 2H negative, where M positive may be lithium positive, sodium positive, potassium positive, rubidium positive, or cesium positive, and M2 positive may be calcium 2 positive, strontium 2 positive, or barium 2 positive. The ionic hydrides have properties that are characteristic of an ionic type compound. These are crystalline, have high melting points, conduct electricity in the molten state, yield H2 at the anode with equivalent amounts of metal at the cathode when the molten salts are electrolyzed. These are insoluble in liquid ammonia and organic solvents. Lithium hydrides are relatively great solubility in organic solvents, indicating a great degree of covalency in the lithium hydrogen bond. Stability of the hydrides depends on several factors. The Born-Haber treatment is presented to illustrate this fact as shown in figure 3.4, where S is equal to heat of sublimation of the metal, IP is equal to ionization potential of the metal, D is equal to bond dissociation energy of hydrogen, EA is equal to electron affinity of hydrogen, U is equal to crystal lattice energy, delta HF degree is equal to standard heat of formation. Thus, here delta HF degree is equal to S plus half D plus EA plus IP plus U. It is clear from the figure 3.4 that the formation of ionic hydride is exothermic as the magnitude of lattice energy U is very large. It can also be inferred as the energy of the product formed is less than the energy of the starting materials. The student should always also be convinced that in this process of hydride formation only, EA, the electron affinity, and U, the lattice energy, are the terms where energy is released. All other terms, namely as sublimation energy, IP, ionization potential, D, dissociation energy, require energy for the halide formation. One can see from figure 3.4 that the value of crystal lattice energy is much larger numerical than the electron affinity. Therefore, it is the lattice energy that determines mainly the reaction to be exothermic. It is important to note that down the group in the periodic table, the numerical stability of the hydride in general decrease. Standard heat of formation of binary hydrides. Hydride, lithium hydride, heat of formation delta HF in kilojoule per mole 90.41. NaH 57.32, KH 56.90, rubidium hydride 50.20, cesium hydride 83.32, magnesium hydride 76.20, calcium hydride 189.25, strontium hydride 177.52, barium hydride 171.67. Hydrides of alkali metals react with water and liberates hydrogen. Example, lithium hydride is used as a source of hydrogen for military purposes and for filling meteorological balloons. Lithium hydride combines with aluminium hydride to form a complex hydride, which is a useful reducing agent. It is ionic in nature. It can reduce carbonyl compounds to alcohols. It reacts violently with water. It is necessary to use absolutely dry organic solvents. AlH4 also reduces a number of inorganic compounds. The elements magnesium, calcium, strontium, and barium all react with hydrogen to form hydrides of the formula MH2. Beryllium hydride is difficult to prepare and less stable than the others. However, impure beryllium hydride was first made by reducing BeCl2 with lithium aluminium hydride. The hydrides are all reducing agents and are hydrolyzed by water and dilute acids with the evolution of hydrogen. The polymeric structure of beryllium hydrides cannot be explained by conventional covalent bonding. Beryllium is bonded to four hydrogen atoms where hydrogen is forming two bonds. The bond between two beryllium atoms and one hydrogen is a special type of bond. This bond resembles to a banana and is called a banana bond. Since two electrons are uniting three atoms, so this bond is also referred as three-center two-electron bond. Next heading 3.7 Solvation and complexion tendencies. Solvation. Alkali metal salts are completely ionized in aqueous solution because of high dielectric constant of water. As a result, the solution of these metal salts conduct electricity. Lithium ion Li positive is small and is expected to conduct electricity better than the solution of same concentration of sodium, potassium, rubidium or cesium ions. This is because the small ions should migrate more easily than the larger ion and therefore conduct more than the larger ions. However, experimentally, it has been found that lithium ion is the slowest moving of all the other alkali metal ions. It is interesting to note that the biggest size cesium ion is the fast moving of all the alkali metal ions. In brief, the ionic mobility and conductivity measurement in aqueous solution of alkali metal ions follow the order. Cesium positive is the highest, then rubidium positive, then potassium positive, then sodium positive, then lithium positive. The reason for the opposite order than the expected is that the ions do not exist as naked ions but are hydrated in aqueous solution. If instead of water some other solvent is used, then we see that ions are hydrated in aqueous solution, that the ions are solvated. Since lithium ion Li positive is the smallest, it is heavily hydrated. This makes the radius of hydrated lithium ion very large and become sluggish to move fast. On the other hand, cesium ion Cs positive is hydrated to a very small extent. Thus, the radius of hydrated cesium ion is smaller than the radius of lithium ion, and therefore the hydrated cesium ion Cs positive moves faster and conduct better electricity. Hydration or solvation involves, in fact, the coordination of water or solvent molecules around the metal ion. Thus, some water molecules touch the metal ion and bind with it and forms a complex. These water molecules immediately surrounding the metal ion constitute the primary hydration shell. In case of lithium ion, lithium positive, the primary hydration shell consists of four water molecules that are tetrahedrally surrounded around lithium ion and can be represented as LiH2O4 ion. Similarly, sodium positive and potassium positive ions may have four coordinated water molecules around them. In case of larger ions, namely rubidium positive and cesium positive, there are six coordinated water molecules around the metal ion. It implies that the hydration number of rubidium positive and cesium positive ions is 6 each. Apart from primary hydration and around the metal ion, there can be secondary hydration of water molecules as well. However, the extent of secondary hydration is inversely proportional to the size of the naked metal ion. Thus, the secondary hydration decreases from the lithium to cesium as the size of ions from lithium to cesium increases. It means that lithium is the most heavily hydrated of the alkali metal ions, whereas cesium is the least hydrated. As hydrated radii decreases with lithium to cesium, ionic mobility increases from lithium to cesium. Ionic radii of hydration of alkali metal ions are given in table 3.7. Thus, the size of aqua lithium ion is distinctly bigger than the other aqua alkali metal ions as shown in the table 3.7. Table 3.7 Ionic radii and hydration of alkali metal ions. Ion. Ionic radius in Armstrong, lithium positive 0.76, sodium positive 1.02, potassium positive 1.38, rubidium positive 1.52, cesium positive 1.67. Hydrated radius in Armstrong, lithium positive 3.40, sodium positive 2.76, potassium positive 2.32, rubidium positive 2.28, cesium positive 2.28. Approximate hydration number: lithium positive 25.30, sodium positive 16.60, potassium positive 10.50, rubidium 10, cesium 9.90. Hydration energy in kilojoule per mole: lithium positive 506, sodium positive 406, potassium positive 333, so rubidium positive 310, cesium positive 276. Ionic mobility at infinite dilution: lithium positive 33.5, sodium positive 43.5, potassium positive 64.5, rubidium positive 67.5, cesium positive 68.0. The hydration number is the average number of water molecules associated with the metal ion. The values need not be whole numbers. The size of the hydrated ion is an important factor that controls the passage of these ions through cell walls. The size of the hydrated ions is also important in cation exchange columns. It has been observed that the hydrated lithium ion are attached less strongly in the exchange columns and are eluted first. Alkaline earth metals ions are much smaller than alkali metal ions. As a result, the hydrational energies of group 2 ions are 4 to 5 times greater than the group 1 metal ions. This is not only due to their small size but also due to their increased charge. However, down the group, the delta H hydration decreases as shown in the table 3.8. Armstrong. Beryllium 2 positive 0.31, magnesium 2 positive 0.72, calcium 2 positive 1, strontium 2 positive 1.18, barium 2 positive 1.35. Hydration energy in kilojoule per mole: barium 2 positive 2494, magnesium 2 positive 1921, calcium 2 positive 1577, strontium 2 positive 1443, barium 2 positive 1305. Complexation: Group 1 metals are different from the other groups in their tendency to form complexes. We have already learned that the factors favoring complex formation are: first, smaller size of the cation; second, high charge; third, empty orbitals of low energy. Group 1 metal ions are very large and have low charge +1, thus these do not prefer to form complexes. However, group 1 metal ions form complexes with some strong chelating agents like salicylaldehyde and acetones. These ligands are very strong complexing agents because these are multi-dentate ligands. Capable of donating more than one donor atom and form a ring or cyclic structure by bonding to the metal. They generally attain a coordination number of 4 or 6 in these compounds. Let us see how salicylaldehyde complexes with the alkaline metal ions. For example, with sodium ion Na positive, it forms the salicylaldehyde complex as follows. Acetylacetone is an important complexing agent. It exists in ketoenol form and it is the enol form that complexes with the alkali metal ion as shown below. It is important to note that sodium ion has attained a coordination number 4 by coordinating with two water molecules. This gives stability to the complex through the attainment of suitable coordination number with a noble gas configuration. The heavier members of alkali metal ions, namely potassium positive, rubidium positive, and cesium positive ions, also form 4 and 6 coordinated compounds with salicylaldehyde. A 6 coordinated compound of potassium with salicylaldehyde is shown in figure 3.6. Please differentiate clearly a covalent and a coordinate bond in these complexes. Crown ethers and cryptands. Crown ethers are macrocyclic polyethers. They are an interesting class of complexing agents. These were synthesized for the first time by Pedersen. These crown ethers have been shown in form of stable complexes with alkali metal cations. A typical example of polycyclic ether is shown in the figure 3.7. The polyether is named dibenzo 18 crown 6 as there are two benzene rings, 18 atoms that make up a crown shaped ring, and 6 of the ring atoms are oxygen. Some of the other important crown ethers used for complexing alkali metals are shown below. The oxygen atoms of the crown ethers complex with the alkali metals. The organic part of the molecule is perchlorate to give the crown arrangement, and the oxygen atoms with their lone pairs are nearly planar about the metal ion at the center of the ring. The nature of bonding between the alkali metal and the oxygen atom of the crown is largely electrostatic. For effective interaction between the metal ion and the crown ether, a close fill between the size of the metal ion and the size of the hole in the center of the polyether is essential. The polyether form complex selectively with the alkali metal ions. It is the size of the ring opening in the crown that determines the size of the metal ion that can be accommodated. In brief, a crown 4 is selective for lithium positive ions. A crown 5 is selective for Na positive ion, and a crown 6 is selective for potassium ions. Cryptatates. Cryptatates are equivalent to crown ethers in their complexing tendencies. Cryptates are polycyclic ligands that contain, in addition to oxygen, other donors like nitrogen as well. A typical example of cryptate is the molecule NCH2, CH2O, CH2, CH2O, CH2, CH2, whole thrice N, as shown in figure 3.8. The name of cryptates comes from the Greek word for hidden. In fact, the cryptate molecule hides the metal ion in its structure. The cryptates are more selective and strong complexing agents than crown ethers. The cryptand 222 can enclose the rubidium ions, rubidium positive completely in a cage and forms a complex rubidium crypt CNS.H2O, in which 6 oxygen atoms and 2 nitrogen atoms bond to the rubidium ion. In this case, the coordination number of rubidium metal ion is 8. In this complex, rubidium ion is surrounded completely by hydrocarbon exterior. As a result, this complex is soluble in organic solvent. You have heard all the time about cationic sodium N positive. Have you ever heard of anionic sodium Na negative? Your answer will definitely be no. But by using these cryptates as complexing agents, you can stabilize the anionic sodium ion, which is called sodide ion. It can be prepared by adding cryptand 222 to cooled a solution of sodium metal in ethylamine. 2Na plus N CH2 CH2O CH2 CH2O CH2 CH2 whole thrice N in the presence of E3N gives out Na CH2 CH2O CH2 CH2O CH2 CH2 whole thrice positive and Na negative, or Na crypt positive Na negative. This Na crypt positive Na negative is a golden yellow diamagnetic solid which is stable only at low temperature -10 degrees Celsius. The interesting feature of the compound is that it contains sodide ion Na negative. Crystallographic studies suggest that the radius of Na negative is 2.3 Armstrong. In fact, electron transfer occurs between two sodium atoms in the formation of sodide ion, as 2Na gives out Na positive plus Na negative. In the presence of 222 cryptand, cationic sodium Na positive will become complexed as Na crypt positive ion. This complex shields completely Na positive ions and prevents it to unite with Na negative ion to form the starting sodium atoms. Difference between crown ethers and cryptands. Both the crown ethers and cryptands have been shown to be versatile complexing agents towards alkali metal ions. However, they differ from each other in the following ways. First, crown ethers have only one type of donor atoms, whereas in cryptands there are more than one type of donor atoms. Example, N and O. Second, crown ethers are monocyclic, whereas cryptands are polycyclic. Cryptands surround and hide the metal ion more strongly. Complexing tendency of alkaline earth metals. Group 2 elements are well known to form divalent ions but are not popular for their tendency to form complexes. If you recall, complex formation is highly favored if the size of the cation is small, highly charged, along with the suitable vacant orbitals of low energy for bond formation. However, group 2 elements are smaller in size compared with the group 1 elements. Thus, group 2 elements should be better at complexing compared with group 1 elements. Beryllium, the first element of group 2, nearly fulfills all the conditions for complex formation and hence forms many complexes. Beryllium difluoride BeF2 readily coordinates with 2 fluoride ions and form the tetrafluoroberylate complex BeF4 2 negative. This ion has the tetrahedral geometry and resembles to sulfate ion SO4 2 negative in many properties. With neutral donor molecules like ether, aldehyde, or ketones, beryllium dichloride forms complexes of the type BeCl2.D2, where D is the donor molecule. Beryllium is known to form many stable chelates with oxalate, beta diketones, nitrates, acetate, and catechols. It is important to note that beryllium in all these cases is tetrahedrally coordinated. The complex of beryllium with oxalate is shown in figure 3.10. A complex with unusual structure is obtained when beryllium hydroxide BeOH2 is evaporated with acetic acid. It is known as basic beryllium acetate. It has an interesting structure where the central oxygen atom is surrounded by 4 beryllium atoms that are located at the 4 corners of tetrahedron. The 6 acetate groups are arranged along the 6 edges of the tetrahedron as shown in figure 3.11. Basic beryllium nitrate can also be prepared by the following sequence of reaction. The structure of basic beryllium nitrate is similar to that of basic beryllium acetate. Basic beryllium acetate is a covalent compound and is soluble in organic solvents. Magnesium also forms a few complexes of the type C2H5 and 2 MgCl4 as in the case of beryllium. However, the higher members are not known to form this type of compounds. Metal complexes are essential in the chemistry of all living species. Perhaps the most important complex on this planet is the magnesium complex called the chlorophyll, the green pigment present in plants. In chlorophyll, the magnesium is at the center of a flat heterocyclic organic ring system called a porphyrin, in which 4 nitrogen atoms are bonded to the magnesium as shown in figure 3.12. Plants and animals derive energy from the oxidation of sugar, glucose with oxygen. Plants are unique, however, as these synthesize glucose from carbon dioxide and water using sunlight as the energy source. This process is initiated by chlorophyll. Calcium and other higher members of group 2 form complexes with a strong complexing agent. Ethyl diamine tetraacetic acid EDTA is a special type of complexing agent which has 4 oxygen and 2 nitrogen donor sites. Thus, it is called hexadenate ligand. EDTA is insoluble in water, but its disodium salt, which is routinely used is soluble in water. EDTA complexes with calcium 2 positive and magnesium 2 positive ions. This process is used for the determination of hardness of water. A representative structure of calcium 2 positive ion complexing with EDTA shown below. Next heading 3.8, Role of alkali metal and alkaline earth metals ions in biological system. Role of Na positive and K positive. Both sodium and potassium ions are essential to life. We need around 1 gram of sodium ion per day in our diet because of our addiction to salt on foods. The intake of many people is as much as 5 times that value. Excessive intake of potassium ion is rarely a problem. In fact, potassium deficiency is very common. Thus, it is important to include potassium-rich foods such as bananas and coffee in our diet. In organic chemistry, we think of similarities between sodium and potassium, but in biology, it is the difference that is more important. Na positive ion is the major ion of extracellular fluids of living organisms which activate certain enzymes in the body. Cells pump sodium ions out of cytoplasm and pump potassium ions in. This ion transport is called sodium pump. It involves both the active expulsion of Na positive and the active lake up of K positive. Analysis of the fluids inside and outside animal cells show that ion transport really occurs. It has been found that the concentration of K positive in the animal cell is about 0.15 m, while the concentration of Na positive is about 0.01 m. In body fluid, the concentration of Na positive and K positive are absent 0.15 m and 0.003 respectively. The energy required for the transport is obtained by the hydrolysis of adenosine triphosphate ATP shown in figure 3.14. It has been estimated that the hydrolysis of an ATP molecule to ADP adenosine diphosphate provides energy sufficient to expel 3 Na positive ions out of the shell and 2 K positive and 1 H positive ions back into the shell. It is important to notice that each operation of the cell expels large number of Na positive ions from the shell than the number of K positive ions that it pumps into the cell. Thus, the cell acquires an excess negative charge and the exterior of the cell acquires a positive charge. It is this difference in the total alkali metal ion concentration inside and outside cells that produces an electrical potential across the cell membrane. The electrical potential is responsible for the functioning of nerve and muscle cells. Role of calcium 2 positive and magnesium 2 positive. Like sodium positive and potassium positive ions, both magnesium 2 positive and calcium 2 positive serve regularity functions. Magnesium 2 positive ions are concentrated in animal cells, whereas calcium 2 positive ions are concentrated in the body fluids outside the cell. The magnesium 2 positive help in the activation of phosphate transfer enzymes, which participates in the energy releasing biochemical process occurring in animal bodies. Mg2 positive and Ca2 positive ions are responsible for the transmission of electrical impulse along the nerve fibers and for the contraction of muscles. Calcium ions are important in blood clotting, and these are required to trigger contraction of muscles, such as those that control the beating of the heart. Certain types of muscle cramps can be prevented by increasing the intake of Ca2 positive ion. The calcium containing compound hydroxyapatite is the main component of the tooth enamel. Cavities in the teeth are formed when acid decomposes the weakly basic apatite coating. This can be prevented, however, by converting hydroxyapatite to more acid resistant coating of fluoroapatite. The source of fluoride ion can be sodium fluoride or sodium monofluorophosphate, commonly known as MFP, in your toothpaste. Next heading 3.9, alkyls and aryls of alkali and alkaline earth metals. Lithium shows a great tendency to form covalent compounds than the other alkali metals, which prefer to form monovalent ionic compounds. Lithium is well known to show the diagonal relationship with magnesium. Magnesium is well known to form alkyl and aryl compounds, popularly called Grignard reagent. It is therefore expected that lithium may also form a number of covalent alkyl aryl which may prove useful in the preparation of a variety of organometallic compounds. Organ Organolithium compounds. Organolithium compounds represent an important class of compounds known as organometallic compounds, which contain at least one metal carbon bond. These compounds have proved versatile reagent in preparative organic and inorganic chemistry. These are used as alkali alkylating or arylating agents for metals and non-metals. These compounds are highly reactive and are sensitive towards air, water, and carbon dioxide. As a result, these compounds are prepared under an inert atmosphere of nitrogen or argon. Alkali metals usually undergo Wood's reaction then treated with organic halides. However, when lithium is made to react with alkyl or aryl halide, the reaction stops at an intermediate stage to give alkyl or aryl lithium derivatives in high yields. The alkyl or aryl lithium compounds are extremely air and water sensitive compounds. These are covalent compounds which can be sublimed or distilled in vacuum. These compounds dissolved in many organic solvents including simple hydrocarbons. The most common used alkyl lithium compounds are methyl lithium and butyl lithium. These can be prepared by the direct reaction of elemental lithium with bromo or idomethane and bromobutane respectively in ether at low temperature. Alkyl or aryl lithium can also be prepared by transmetallation reaction between lithium and organomercury compounds. A wide variety of organolithium compounds can be prepared by lithium halogen or lithium hydrogen exchange reaction using N-butyl lithium. In the reaction, lithium is transferred to alkyl or aryl group having the higher electronegativity. For example, properties. Organolithium compounds have been found to be more reactive than the well-known Grignard reagent. These have extensively been used as alkylating or arylating agents for both metals and non-metals. Some of the important reactions of these versatile compounds are given below. First, reaction with carbon dioxide. Organolithium compounds react with carbon dioxide, even atmospheric carbon dioxide, to give carboxylic acid. Second, reaction with metal halides. Organolithium compounds combine with metal halides to form a variety of organometallic compounds. Third, reaction with halogen. Organolithium or compounds react with halogens and afford alkyl or aryl halides. Fourth, reaction with alkyl iodides. Organolithium compounds react with alkyl iodides and give coupled products. Fifth, reaction with acids. Organolithium compounds react with acids and form the corresponding hydrocarbon. Sixth, reaction with N or N disubstituted amides. Organolithium compounds react with N disubstituted amides to give aldehydes and ketones. Symmetrical ketones are formed when organolithium compounds combine with carbon monoxide. Seventh, action of heat. Organolithium compounds on heating decompose to give lithium hydride and an alkene. Eighth, metallation reaction. Organolithium compounds can metallate easily compounds with acidic hydrogen. Ninth, reaction with sulfur. Organolithium reagents combine with sulfur cleanly, which upon acidic hydrolysis afford mercaptans. Structure of alkyl lithium compounds. Alkyl lithium compounds are covalent in nature. These compounds are frequently tetrameric or hexameric. Methyl lithium exists in the solid state as a tetramer CH3Li4 as shown in the figure 3.15. The four lithium atoms in the structure occupy the four corners of a tetrahedron. Each methyl carbon atom is above the face of a tetrahedron and forms a triple bridge to the three lithium atoms that make up the face of a tetrahedron. The carbon atom is bonded to three hydrogen atoms in the methyl group. It is also bonded to an additional lithium atom in other tetrahedron. Thus, the coordination number of carbon is 7. This cannot be explained by conventional theories of bonding because carbon atom has only one s and 3 p orbitals available for bonding. In fact, the bonding involves 4-center 2-electron bond covering the three lithium atoms at the corners of a face and the carbon atom above it. Similarly, the coordination number of lithium is also 7, which is made up of 3 lithium in the tetrahedron, 3 carbon at the center of faces of a tetrahedron, and 1 lithium in another tetrahedron. Alkyl lithium compounds are electron deficient compounds and involves multi-center bonds as in the case of boron compounds. These compounds generally exist as tetrameric or hexameric. In the presence of nitrogen donor bases, these compounds exist as monomers. Some of the typical reactions of organolithium compounds are summarized below. Rx plus lithium in the presence of ether or hydrocarbon gives out LiR, which is when reacted with HCO and Me2 gives out RHO, with HgBr2 gives out R2Hg, which with halogen and X2 gives out Rx, with Ri gives out Rr, with CO and H positive gives out RCOOH, with with BCl3 gives Br3, with SnCl4 gives Cl4 minus X, and SnRx where X is equal to 1 to 4, With H positive, it gives RH. With in the presence of heat, it gives olefin plus LiH. In the presence of CO, it gives R2CO, and in the presence of RSCO and Me2, it gives out RSCOR. Organosodium and organopotassium compounds. Organosodium and potassium compounds are appreciably ionic. They are highly reactive towards air and moisture and are pyrophoric. These are prepared by transmetallation reaction involving organomercury compound as. Because organosodium and potassium compounds are highly reactive, these are preferred to be prepared in C2. It means they are not isolated. These are also prepared from the hydrocarbons with acidic hydrogen atom. The high reactivity of these compounds has been exploited for the preparation of many transition metal organometallic compounds. Organoberyllium compounds. Beryllium forms a number of organometallic compounds with MC bonds. However, a few compounds have been isolated for calcium, strontium, and beryllium. Let us first discuss the organic compounds of beryllium. Preparation. Organoberyllium compounds are prepared by reacting beryllium chloride either with alkyl lithium or Grignard reagent. This can also be prepared by the reacting beryllium metal with organomercury compounds by transmetallation reaction. Properties. First, dimethyl beryllium is a white polymeric solid. Other alkyls of beryllium are usually dimeric. Bulky groups makes the bridging unstable and the compounds are monomeric. For example, the sterically hindered of ditert butyl beryllium is a monomer under normal conditions. Second, dialkyl beryllium combines with alcohols and yields corresponding alkoxide. The methoxide and ethoxide of beryllium are polymeric, whereas the butoxide of beryllium is trimer soluble in benzene or hexane. Third, dialkyl berylliums are spontaneous flammable in air. Fourth, dialkyl berylliums are immediately and explosively hydrolyzed by water. Fifth, dimethyl beryllium, when reacted with ethylene oxide, opens the ethylene oxide rings. Sixth, dimethyl beryllium reacts with tert butyl peroxide to give the alkyl beryllium alkoxide according. Structure. Alkyl beryllium compounds are polymeric in nature. The lower members, dimethyl beryllium and diethyl beryllium, are polymeric, whereas the higher members like tert butyl beryllium are monomeric, as shown in figure 3.16. Organomagnesium compounds R2Mg. R is equal to alkyl or aryl. Preparation. Dialkyl or diaryl magnesium can be prepared by the reaction of alkyl or aryl lithium with Grignard reagent. This can also be prepared by the reaction of organomercury compounds directly with activated magnesium. On a large scale, organomagnesium compounds are prepared by reacting alkenes with magnesium in the presence of hydrogen and under pressure. Properties. Dimethyl magnesium Me2Mg is a white involatile polymeric solid which is insoluble in hydrocarbon and only slightly soluble in ether. Diphenyl magnesium PH2Mg is insoluble in benzenes but dissolves in ether to give a monomeric complex PH2Mg.2Et2O. Second, dialkyl magnesium reacts with alcohol and ketones to give alkyl magnesium alkoxides. Structure. The structure of dimethyl magnesium is similar to that of dimethyl beryllium as shown in figure 3.17. Organomagnesium halide RMgX. Perhaps one of the most versatile reagents used in organic chemistry is concerned with organomagnesium halides. These are called Grignard reagent after its discovery. Victor Grignard, who was awarded the Nobel Prize in Chemistry in 1912. Grignard reagents are household name for all practicing chemists. These reagents can be used to prepare a variety of organic and organometallic compounds. Preparation. Grignard reagents are prepared by the slow addition of an alkyl or aryl halide to a continuously stirred mixture of activated magnesium turnings in anhydrous diethyl ether. The reaction is slow in the beginning because the surface of magnesium is coated with a thin layer of magnesium oxide. Very often, traces of iodine are used to initiate the reaction. The order of chemical reactivity of alkyl halide is iodine the highest, then bromine, then chlorine. Grignard reagents are very reactive, especially towards oxygen and moisture. As a result, these are not stored and are made and used afresh. Properties: first, all Grignard reagents, either alkyl or aryl, are rapidly hydrolyzed by water. They react with water and give the parent hydrocarbon. Second, Grignard reagent can be employed to prepare a variety of compounds as listed below. Third, Grignard reagent can be used to prepare a new variety of organometallic compounds. Fourth, Grignard reagent react with ethylene oxide to give alcohols. Structure: Grignard reagents are represented by the simple formula RMgX. These are in fact normally solvated or polymerized with halogen bridges. X-ray structure of PHMgBr.2ETO ET2O and ETMgBr.2 ET2O suggests the magnesium is tetrahedrally coordinated by bromine, the organic group, and oxygen atoms from ether molecule as shown in figure 3.18. However, in solution, several species may be present in which the magnesium atoms are probably linked by halogen bridges. The extent of polymerization depends not only upon the concentration of Grignard reagent but also on the solvent and the halide used. In strongly coordinating solvents such as ET3N or THF tetrahydrofuran, Grignard reagents are monomeric, presumably because Mgn and MgO bonds in solvated monomers are more stronger than the magnesium halogen bridges. Grignard reagent can disproportionate according as. However, in simple ethers as a solvent, there is little or no evidence for the formation of significant amount of either R2Mg or MgX2. On the other hand, a solvent which complexes more strongly with one member of the above equilibrium then the other two can cause the equilibrium to shift to the right hand side, such as displacement occurs when dioxane is added to ether solution of a Grignard reagent, a precipitate of MgX2.2 C4H8O2 being formed. The whole sequence can be presented as given below. So this was all about S block.